We have plenty of time. We have all weekend. Figure out what Galois is.
Which we can optimize her time from getting from place to place to an undergrad.
I see. Yeah. Should know how to run all their house.
Yeah.
Yeah. Do you ever take the bus? Do you ever take the bus to get between classes here?
Well, because there's no real pathways of that. So,
Yeah.
and then you have to wait.
Yeah, at the University of Minnesota, there are 3 campuses. 2 of them are split by a river, and the third one's in a different city. Shows buses between all these places.
This is a 1 mile per 1 mile square.
Oh, really? I didn't know that. I go somewhere.
All right, welcome back, everyone, for the afternoon session. One thing that happens in the math department every year is that you saw the courtyard, right? It has a little inside region as well. You can't get out. And every year there's a duck which lays its eggs. So if we didn't have a lecture right now, as of this moment at 2 p.m., we have to escort the ducks with the ducklings from the math department through the building out to the lake. That's a little thing. And it's been going on for at least as long as I've been here. But in any case, let's welcome John Bergdall to talk about Galois representations.
Okay, so thank you for the chance to speak at the summer school. I'm going to give 4 lectures on Galois representations and eigenvarieties. And the way they're going to work is the first lecture is going to be on Galois representations, mostly examples. And through these examples, I'm going to introduce the idea of a p-adic family, which is what an eigenvariety really is. It's a p-adic family of automorphic forms. Then the next lecture will cover kind of an introduction to those things. The third lecture, I'll come back to the theory of Galois representations, and on the 4th lecture, I'll go back to the theory of eigenvarieties. As I go through the lectures, if you have questions, feel free to raise your hand and say something, or just put a star in your notebook where you had a question, and then you can show me the notebook later, and I'll try to figure out what question you had. Okay. It's better if you write down your question. Good. Our representation. So I want to start with the Galois group. Galois groups, I mean, I could do this in some generality, but I'm actually going to get everything existing over the rational numbers for my lectures. So I'm going to write QR, the field of algebraic numbers. Some of these notations already showed up in purposes around slot this morning. The Galois group of the rationals is the Galois group of the algebraic numbers over the rational, so they're field automorphisms from the algebraic numbers to themselves, lying over the rational. Okay, and this is a group, but it's also a topological group. Okay, so this also came up earlier. I think even in Nadir's talk, it was mentioned that the Galois group is a compact group. Let me just describe the topology for you. There's a basis of open neighborhoods of the identity element, 1 inside the Galois group, is following collection. You take the Galois group, Q bar over F, where F is an intermediate extension between the rational and the algebraic numbers, such that the initial extension it's finite. So you take all the automorphisms, the algebraic numbers that don't just fix Q, but rather fix some finite extension, some number field sitting above Q, and that forms an open basis. That forms open neighborhoods of the identity, and then a general open set. And the topology is then generated by translation inside the group. Let's take out a group. It's a topological group topology. And the trick is that as you work through the theory more and more, and as you become more and more advanced and you're doing research, you kind of forget about this topology because it's so innate. But in the beginning, it's nice to pay attention to it for a while. So I'd like to begin discussing representations by using this topology a little bit, just to describe the complex characters on the Galois. What are the complex one-dimensional representations? Good. Does anyone know? I said, I mean, money start dependent, and we'll see where we go from there. Opposition. You take a continuous character, continuous homomorphism from the Galois group into the complex numbers, then chi has finite image. Good. And then at that point, chi is essentially a Dirichlet character. It's factoring through the Galois group of the atomic field, and maybe there's some exercise involving the idealization of a Dirichlet character, and also the realization of them as Galois characters that we kind of work through later. Like I said, I wanted to put this on the board so that we could think a little bit about the topology. And the proof is essentially to realize that this topology on this Galois group has the property that there's smaller and smaller open sets that are also subgroups. And that's exactly what the complex numbers don't have. Okay? And because of that, there can't be too many maps between them. Okay? So if you look at set U, which is the set of complex numbers that are non-zero, okay, it would be defined by this inequality anyways. The complex numbers who are, small ball around 1. So here's Z as 1. And my open set U is there, that's in the complex plane. Then this has the property that the only subgroup inside U is the group consisting of just the identity elements. And that's because U is a bounded subset of the complex plane, and any bounded subset, any bounded subgroup of the complex plane would have to be contained within the unit circle. And now if you picture a non-identity element in the unit circle inside U, and you just take some large power of it, it like eventually escapes U. And therefore it can't be completely contained within U. Okay, and then, so what does that mean? On the other hand, if you have a continuous character, then the preimage of this open set would be open. So chi inverse of U contains one of these finite index subgroups, the Galois group, finite index open subgroup, or somehow it's equivalent because the groups come back. And then the image of this under chi would have to be a subgroup inside U, which then must be only the identity element. And so this implies that the Galois group Q bar over F is contained in the kernel of chi, which is to say chi factors through a finite quotient of the Galois group, which is to say that the image of chi is a finite subgroup of C cross. Okay. So it's the kind of proof I can remember even after years of kind of doing a lot of research. This is really one proof I go back to over and over again whenever I think about the theory of Galois representations. The way I'm going to structure my lecture is I'm often going to go through theory and examples kind of interweaving with each other, and now I want to introduce some terms. So maybe if there's any questions, I can pause for a second. Okay. Well, if you do have questions, make sure you speak up or mark them in your notes. The next topic I want to talk about is ramification. Sorry, that's not the next topic I want to talk about. I want to talk about the prime by prime structure. So we saw this in Rajaram's lectures this morning when he was talking about local factors of a Dirichlet character. And Nadir also began to explain this sort of at the end of his lecture. So this will be a good review of that also. I'm going to fix a prime L. Okay, that's right. I'm going to fix a prime L, and then I'm going to make a choice of ways of embedding the algebraic numbers into an algebraic closure of the L-adic numbers. That's really a choice. You have many different choices to do that, and the different choices are called the L-adic places of the algebraic numbers. Okay. Any choice is defined under an automorphism of Q bar, though. And one of the basic facts is that what I can do now is take a Galois element for the L-adic field, and I can restrict it then along this embedding, this kind of arbitrary embedding that I've chosen. And this map will actually always be injected, and it identifies actually the image with the automorphisms of Q bar that are continuous for the topology induced by that inclusion. Okay. This is some injected. And it's only, this is because the choice of these embeddings differ by automorphisms of Q bar, the choice of this group embedding is defined up to conjugation inside the absolute Galois. Okay. And in research papers, you often see people just like write subset here, and hopefully throughout the rest of the paper, they only ever do things that is conjugacy invariant on that group. They take traces of elements in representations and things like that. But anyways, this kind of gives a small piece of this Galois group that depends on the prime L, and that piece further decomposes, as in Nadir's lectures, according to an exact sequence, where the absolute Galois group, the L-adic field, maps onto the absolute Galois group, the finite field with L elements. The kernel of this map is called the inertial subgroup. Here's this inertial subgroup. What else do I want to say? This group is topologically cyclic. So it's generated topologically for the same topology that I wrote down there by the L power map. That's the Frobenius from Nadir's talk. And I choose to write prob L. Sorry, this is like an automorphism, and this means it's generated, and prob L is any lift of that. So again, like this, the symbol prob L you see over and over again in research papers is not an actual thing that exists. It's a concept that exists, and it's a concept that's only defined up to conjugacy and the inertial subgroup. This is defined up to IL and conjugacy. Okay. Good. Now I can do what I was going to do before. After talking about this prime by prime structure, which I think of these Frobenius elements as very much the same as the local factors of Hecke characters, for instance, from Rajaram's talk, or the local factors of automorphic representations. I can discuss the idea of ramification. The following. And then after this, I'll go back to another example. Okay, so I'm kind of throwing some terms at you now, and then we'll do an example. I'm going to make a definition. So if you take a map from the Galois group to H, this is any group. I'm going to call it rho because rho is the natural letter for me for representation later. We say that this is unramified at L. if IL is contained in the kernel of rho. Okay, that's a definition. And warning, the definition defines what it means for a prime L to be unramified, but it's phrased in terms of this inertial subgroup, which is not a well-defined thing. It's only well-defined over the conjugacy. So the first comment you need to make is that this containment only depends on L, because this is a normal subgroup. Okay, so no matter what conjugate representative you pick, they'll all be contained in the kernel. Once. That's an important point to make. Let's connect it with algebraic number theory. So for example, let's take the projection. So if you take a Galois extension, and there's a projection from the absolute Galois group onto this finite group, say, finite Galois. And when is that projection unramified at L? The projection is unramified at L exactly when L is unramified in the field map. Unramified at L. You can only if L is unramified in the sense of algebraic number theory. At it's an example to keep in mind. It generalizes the basic notion of unramified. A field extension being unramified at a prime. And the other thing I want to say has to do with these Frobenius elements now. That if rho is unramified at L, then rho of prob L. I mean, actually, let me quote around it. Why did I do that? There's a precise statement I can make. Then the conjugacy class of rho of prob L depends only on L. Okay, so if you take a group homomorphism that's unramified at a prime L, then you can speak of rho of prob L as long as you remember that it's only a conjugacy class in by the target, whatever the target may be. Okay. Are there any questions about what I've said so far? Space. So I introduced the Galois group. This is kind of an example. I know that it's like a theorem, but it's kind of an example. And this is a bunch of terminology. So now I want to go through that terminology in an actual example. The kind where you could put numbers down if you wanted. This is the example of the cyclotomic character. Good. So I'm going to fix P now prime. And this is, I don't actually know what's going to happen in the other courses, but for someone that studied p-adic things, P is a distinguished prime that's really important, and L is a prime that varies. Okay, so that's something to keep it in mind. I think the prime, and yeah, maybe I should also figure the root of unity. Let me be really concrete about this. E to the 2 pi I, a p to the nth root of unity. So I fix primitive p to the nth root of unity. Then the absolute Galois group of the rationals projects onto the Galois group of the p to the nth cyclotomic field by restriction. And this group is isomorphic to the units in Z mod p to the n cross by the map that sends an integer a representing a congruence class here to the automorphism that sends p to the n root of 1 to its 8th power. Okay. Good. And okay, and then there's some composition. And so then I get a character called chi-n. I'm just calling it chi-n. This thing doesn't really have a name in reality, I would say. And actually, it's kind of one of these things here. But I'm going to do something with it now that you can't do with those things. I'm going to turn it into an infinite image, one-dimensional representation. So proposition, each chi-n is continuous. And the glue, I don't know if that's the right word, I'll put it in quotes so that you can ask me what I mean. They glue to define, not be the best one there, define cyclotomic character is called, which is the character of the Galois group, which is continuous. It surjects onto the units in CP cross, the multiplicative group of the p-adic integers, which is, say, for the purposes of this proposition, making it as easy as possible to prove, the projective limit of the unit mod p to the n, as n radians. And so this character is unramified at which L? Yeah, yeah, what?
Yeah, that is away from.
L is different than P, exactly. It's unramified at L different than P. And what is the value of a Frobenius element then? So chi cyclo Bergdall. Remember, the image of Frobenius is a well-defined conjugacy class, once I'm unramified, but the target here is abelian, so it's a well-defined element. That element then is a number, a p-adic number. And what p-adic number is it? Let's look at the Frobenius element over there. The Frobenius element is like, well, technically it's not L power map, it's kind of lifting the L power map. And let's look at this. What are these automorphisms? They're kind of raising to the A power. The Frobenius map could be the L power map here. So it would correspond to the number L here. Good. So that's nice. I'm not going to actually write this proof out. We just proved like half of it. Basically, let's go back for a second. Why is it unramified at L different than P? Well, all of these projected maps are unramified at L different than P because these projected maps fall into my first example over here of when is a projection map unramified, and the prime L is unramified in that cyclotomic field. Why is the cyclotomic character a continuous character? Well, that's once you assume the first part, that's the universal property of this projective limit. And now why are these finite things continuous? Well, they're continuous. I didn't tell you the topology here. What topology am I putting on the target here? The discrete topology is a finite group. Okay, so this is the discrete topology, and so the second character is continuous. I just need to check that it has open kernel. But the kernel of this map is literally the Galois group fixing the cyclotomic, which is by definition one of my open subgroups. Okay. So it's a fairly complicated statement that with a little bit of courage can be proven. Good. I'm going to do something not everyone is expecting now. I'm going to go with p-adic family of these characters. So, yeah, I mean, please. Sorry, I just returned from Germany 3 weeks ago, and I can't. Go ahead, Roger.
That L is unramified. Not P. So this depends on computing the discriminant of Q zeta P.
Yeah.
I'm just trying to remind myself.
Why is L unramified in the cyclotomic field?
Yeah, so
I have to also remember why, other than it's just a fact that I have so internalized that the primes of ramification in the n cyclotomic field are the primes dividing that.
Discriminant is the power of P, right?
Yeah,
I think so.
if n is A times P and A and B are relatively prime, then you play with this kind of fields which are linearly disjoint and it suffices to just pick up
comes down to just p power.
Yeah.
And then for p power, and you just have to do some calculation.
I think you write down the single-tone the p-adic single-tone polynomial, and you probably compute the derivative or whatever you need to compute. Yeah, I
Inertia is that when you apply to an element, you get a congruent element. So I guess the exercise you have to show to solve is that like delta n to the power is congruent to. I mean, that's very good exercise for the problem session.
Yeah, and anything, it's a good exercise in remembering algebraic number theory. Which, I'm not saying that in a demeaning way, I'm celebrating the idea that I don't remember how to compute discriminants off the top of my head. I spent too much time building p-adic families of automatic forms of this kind of thing. Let's build a p-adic family. So this is going to come up throughout my lecture, and certainly Milana's lecture as well. Let me say p-adic analytic family. Here's the word analytic. And this is not a standard topic you would see in an introduction to Galois presentations. It's really custom for where I want to go in the course. So let's take the units on dp cross. And let's take any continuous character of the p-adic units. Then I can compose it with the cyclotomic character, and I get a new Galois character. So I think I need to do the cyclotomic character first. A new Galois character. So for example, you could take algebraic characters of the p-adic units, which are the power maps, or kappa of x. Is x to the n. And in Z, this might be what I call an algebraic character. Then of course, the composition is the n power of the cyclotomic character. Which is something you probably already understood you could do to the cyclotomic character to take its powers. For a second example, let me just take the prime difference in the two so that what I write is true. You can modify it by using a different description of the units, the p-adic units. And I take a p-adic number s. So in the L function story, there's always this f variable, and this is somehow the same f, except it's a p-adic number rather than a complex number. And then I can make the following construction. So I can take the p-adic units, and there's always a way of projecting onto the one units by dividing by a p minus first root of unity. Okay, so there's kind of this decomposition of dp cross into one unit and an origin part. And then on the one units, yeah. I mean, I'm going to go to 1 plus pdp again, so let me just write dp cross. There's a map I can take, which is y goes to y to the s. So you can take a one unit in CP and you can raise it to a p-adic power. Now I should say a little bit about what this means, and this will come up in the lattice also. So let me get a little bit carefully. So here, y s is defined as times the p-adic logarithm of y, where the p-adic logarithm of y means you take y and you plug it in the power series expansion for the logarithm centered at 1. And that power series will expand, that power series expansion will converge in the p-adic topology because y is close to 1 in the p-adic topology, being a 1 unit. Okay? Once you do that, you'll actually, this is super important for this formula to make sense. The number you get will be divisible by p when you take the p-adic logarithm. And then regardless of what s is, the exponential will actually converge. The power series for the exponential. So there's some p-adic analysis that, to be honest, I went through when writing these notes, and I'm reminding you of. And it might be worth going over later as well. Okay. Actually, I want to use that space a little bit. This. And so now, based on this, so that could be one of my kappas. Okay, my kappa could be like the S power map, except technically you have to project on the 1 units. Yeah, that's a question.
Yeah, what's the first map between ZP star and 1 plus PZP?
Yeah, it's a projection, like. CP cross all its factors. In a, what we would call a canonical way, into the units in FP. Plus 1 plus PZP. Like how to say this, like,
Oh,
the units in FP are P minus first group of unity. And by Hensel's lemma, they lift uniquely to DP cross. And so there's a copy of the P minus first group of unity inside here. And then there's a splitting of that onto the 1 units. Okay. I'm trying to think if there's a better, there's not like a formula for this thing. It's part of the problem. Like this is a sum of this naturally, and this is the quotient of this naturally. And as an abelian group, it decomposes into a direct product. Okay. Yeah, so unfortunately, there's not a formula for this that I can write down other than kind of writing out a formula for how this is a sum of this, which in theory kind of involves tensile sum. Okay. Yeah. I mean, these are all a lot of things to keep track of, so I appreciate the question.
I mean, that complicated as trying to make consistent, not exclude.
Yeah, so the comments just for the audio is as complicated as making Hensel's lemma explicit. Like you can't really write down a formula, but you kind of prove something exists and prove properties of it without ever really touching formulas, I would say. Okay.
Like it's converging with Christian graphs.
And so now you get a universal character. I don't mean the universal character, I mean and it's universal for the power maps. What I call it. Angle dot universal, and it's a character from ZP cross into the power series ring over ZP in the variable S, and it's given by the formula I just told you. It's given by the exponential of S times log of Y. So given by X universal. Is the sum n goes from 0 to infinity, I guess, of the p-adic logarithm of the 1 unit to the n over n factorial s to the n. Okay, and this series will converge on the p-adic norm of x is less than or equal to 1. Why? Let me say a little bit of why it's true. So Milan reminded me to remind you of all this. That for an infinite sum to converge in the p-adic topology, the only thing you need to check is that the general term is going to 0 in the p-adic topology. But if you look here, this p-adic logarithm has a p in it. And then you're taking n power, so there's at least p to the n here, and the p to the n's dominate the n factorials. So these kind of things are already going to 0. And then anything of norm 1 can't stop that from happening, norm less than or equal to 1. So the series will converge on that domain, and maybe even a slightly larger domain. Technically, when you specialize it to an actual p-adic number here, like if you plug in an s, you'll get exactly this character here, kind of by definition, that's all there's on. And yeah, I did want to say that this thing here is congruent with 1 mod t for the reasons I've already said. Although if you expand it to the power series, the 0 term is 1. And everything else has a p in it because of that p-adic law. And so what this is an analytic family, because it's a power series character of different p-adic characters, all of which are congruent to the trivial character mod p. The basic example of a p-adic affirmation of a character, or a p-adic analytic family of characters. Probably not what anyone necessarily thought they were going to see when they woke up this morning. Good. So after the cyclotonic character and its analytic family in some sense, I think I want to do another example. Right? Yeah, I want to talk about elliptic curve for a minute. I know some of you have studied elliptic curves, so I want to just write on the board that kind of example. See where we get after that. Actually, I really like the way this works for before, so if you don't mind, I'm gonna erase 2 boards at once. As I'm doing this, feel free to ask questions.
The universal family of characters,
I mean,
like, is that the universal deformation or?
no. No. So for one thing, so, yeah, we'll talk, you'll see some deformation, I'll say something about the deformation phase in a minute. And, let me just say, like, well, first of all, what do I want to say? I mean, somehow it is, but like you would have to expand the domain slightly to make sense of that, maybe. Okay. Let's talk about that question later, because I'm not quite sure what the answer is off the top of my head now that I think about it. What I meant more was that it's universal for these particular characters. That when you specialize for one of the actual S's, you get back the one that I wrote down. Okay. So I've taken a look at curve, you over the rational numbers. Then I can talk about its p-torsion points. So these are the points defined by the algebraic closure of Q that vanish under the p power map on, not the p power map, the multiplication by p map on the curve. And maybe if you think about it, look at curves as complex numbers modulo a lattice, it's the most clear way to understand that as an abelian group, the p-torsion points on the elliptic curve are 2 copies of Z mod p. It's some p-torsion group, it's finite, and it has rank 2 over Z. But very importantly, the Galois group acts on the key bar points of an elliptic curve by substitution in the variables. And the Galois group commutes with the group law. This is part of the theory of elliptic curves. And so the Galois group acts on this thing in a manner compatible with the group structure here. And so what you get now is your first example of really a Galois representation. So it's a map rho bar E into GL2 of FP, which I'm identifying with the automorphism group of the p-torsion. The automorphism of the Z mod P as a Z mod, the Z mod P squared as a Z mod P vector space is GL2 of FP. And this is a continuous. This is a continuous map of the Galois group. Let me just say, you can think about that as one of the exercises maybe and ask me if you're not sure. In this example, I don't need to only talk about p-torsion. In this example, I was looking at the p-adic root of unity, which was a torsion, p-power torsion on the circle. And here I replace the circle with the elliptic curve. So I can also talk about p-power torsion on that. So you have a whole power torsion subgroups. P squared torsion, cube torsion, so on. And the limit of all the p to the n torsion is now 2 copies of the p-adic integers because it's the projective limit of the Z mod p to the n squared. So you get a representation without a bar now. So the bar means mod p, and now you have one without a bar. And it's a continuous representation from the Galois group into GL2 of ZP. Automorphism of ZP squared as a ZP model. All right. Proposition rho E is continuous. But essentially, for the same reason why all of these are continuous in some universal property, it's semi-simple. So there was a whole discussion of semi-simplicity that occurred at the end of the last lecture. Actually, maybe before I do that, I get a little bit confused about things with integers versus over a field. So let me make it over a field and then say it's semi-simple. But that's just my own possibly pedantic thing to do. It's continuous and semi-simple. It's unramified. At L different than P, where E has good reduction. So remember, an elliptic curve is given by a cubic equation, say, defined by the integers. Maybe there's some minimal kind of Weierstrass equation, and that curve could be non-singular or not modulo L. You have good reduction when you're non-singular. It happens for almost all L. And when that happens for an L, and that L happens to not be P, then this Galois representation will be unramified. And when that happens, then we can talk about the Frobenius element over here. But now I want to go back to this comment. You have to be a little bit careful. The Frobenius element will be a 2x2 matrix, which is only defined as the conjugacy. So whatever I write down now has to be conjugacy invariant. And what I can say is that the characteristic polynomial of rho of Bergdall, which is definitely conjugacy invariant of a matrix, is x squared minus AL of the x plus L, where here AL is L plus 1 minus the number of points on the curve. Okay. Good. Now, the main highlight here, actually, you can kind of really start to connect things, right? So I call this the prime by prime structure over here, and I'm kind of talking about the image of these groups here and the Frobenius elements as being kind of corresponding to local information somehow. And here what you see is the Galois representation is some object coming from global arithmetic, in the sense that you start with a curve defined over the rational numbers, you take torsion over the rational numbers, you take that action of the rational Galois group. But when you look at the prime by prime structure, the prime by prime structure sees prime by prime structure on the global arithmetic of the curve. It sees essentially the point counting and all the finding primes of the curve. And I'm going to say that here among automorphic representations, where you'll see a similar kind of behavior. So are there any questions before I move on to the final, basically 3 sections to talk, the final 3 topics? I guess I did have a comment about the proof. The proof, like, I cannot sketch the proof of this off the top of my head the way I can sketch the proof of that off the top of my head, because this fundamentally relies on theorems of automatic curves. This is not just like some kind of thing you can just do mucking around with algebra. You have to prove theorems of automatic curves to prove this kind of thing. Which is only to say that when you think about automorphic forms and representations later, you really need to have a lot of expertise to really prove those kinds of things. On the other hand, I'm completely an expert in using Galois representations like this, like as a researcher. And I don't need to understand the proof of this theorem at all to do that. So maybe that's a good thing. Let me give you an example. Actually, let me write down the question. Families. So an example of an elliptic curve is the curve of x naught 11, which I think in the notation from Argon's talk would be the upper half plane modulo gamma naught 11, except maybe you have to add a point at infinity, or 2 points at infinity actually, because this will be a non-compact curve. You don't have to do it that way though, like it has an equation. Comes in that Weierstrass form. I want to say, there's permanence. So it has grid reduction. At L greater than 11. Somehow there's an 11 here, and that's related. What else do I want to say about the curve? Let me just give you a few point counts. So A2 of E, -2, A3 of E, -1. These are all things, by the way, if I just look at the computer, I could show you on the computer, like typing computer algebra system. There's an infinite amount of curves, and each of them have their own arithmetic, and the computer is really useful for seeing those things. This representation here, this mod P representation, let me say something about that. I look at rho bar, which is rho bar of E. That's acting on a two-dimensional FP vector space. That action is irreducible. Almost always, that's a theorem about any elliptic curve. There's some uniform bound after which it's conjectured to be true. And for this particular example, sorry, I misspoke this. The fact that this action is irreducible for almost all P is only a theorem about curves without complex multiplication. But this curve doesn't have complex multiplication, so that's one of them. This particular one has an irreducible action. When P doesn't equal pi. Okay. That's just some little example, which is to say that if you're sitting down and doing research on your own and you need some example, you might remember this in your notes. What does that have to do with family? So Mazur in the 1980s, thinking about my second lecture actually. Yeah.
Can you give some reference to what details is done? Especially the last statement. Is not five.
I don't know the references off the top of my head, but I think I checked this using an internet search engine that rhymes with Google while I was preparing the lectures. Yeah, I mean, I don't like it's not how do you calculate this?
First by Mazur's theorem, I mean, you know, it's
Yeah.
reducible like if P is bigger than 163 anyway. So it's a finite statement. And then for each one, you can just on magma pull up some traces. And
I was particularly wanting to know, so these five, then what happened? There's some congruence between
Yeah.
this and some others.
If P is 5, there's a congruence between this curve and an Eisenstein series, exactly.
Yeah, so where can I look that up?
I would Mazur's paper. Mazur wrote a paper in 1977 called. Oh, I don't know what it's called. It's the paper, the Eisenstein ideal paper is what it's called.
and another way, you write your Eisenstein series and P probably divides the constant term or something. So it's gotta be a congruence.
Yeah, I don't. Let me think of how you might check this, like if you didn't know to check something about Eisenstein series. I think the best way to explain. So Mazur in the 1980s invented building on kind of theories of p-adic families that he had already developed in the automorphic picture. Something called deformation spaces. So when rho bar, and I assume it's one of these ones associated with elliptic curve, so that I don't have to write a whole bunch of hypotheses at this point, is irreducible, then Mazur invented something called the deformation space, it's called X rho bar. A deformation space, I'm going to put that in quotes because I don't have any intention of explaining exactly what it is. You should think of it for now as a p-adic manifold. Something locally kind of that looks like powers of ZP. Some number of copies of them. ZP is like an affine chart or some ZP cubes, just to the fourth or something like that. And I can tell you though, maybe if I think about it as a formal scheme or p-adic rigid analytic space, what its ZP points would be. So its point over the p-adic integers will be the deformations of your row bar. So GL2 of ZP maps onto, that's not a very good GL2 of GP maps onto GL2 of FP. You have your row bar, which is a representation here, and the deformation space at the level of points over DP collects the information of any possible bits here. There's rows here. So this is row bar E. And the deformation space is the collection of all those bits up to an equivalent version. Okay. Now, it's just like a set or something like that. So the role I want to have to play in this talk is that a theorem that Mazur proves in the original paper in the 1980s is that this space, this geometric space, always sits as a closed subset of a 3 ball over ZP, a 3-dimensional ball. Okay. Kind of defined over ZP, or if you think of it really as a p-adic manifold where P is inverted, then it would just be a 3-dimensional ball in that sense. And for instance, in this example, when P is larger than 13, these I do know the precise references somehow. Once P is larger than 13, it'll really be isomorphic to a 3 ball. Okay. Now,
I have two questions.
yeah,
First of all, is that map, is it a closed embedding?
yeah.
Okay.
Wait, what do I mean? Did I write it right? This should be 4-dimensional, so it should be sitting inside 3-dimensional space as a 3-dimensional thing.
Well, it's 3-dimensional over ZP.
Yeah.
3-dimensional.
Yeah, it's 3-dimensional over ZP. So on the affine side, this is represented by a ring that's a quotient of a power series in 3 variables over ZP.
Also, why was Mazur interested in sort of parameterizing these lifts in this very specific way?
So in the next lecture, I'll talk a little bit about eigenvarieties and families. And in this theory, you have not Galois representations moving by first principle, but you have modular forms moving by first principle. And modular forms have Galois representations associated with that. And he proves in his work in the 1980s that the Galois representations associated with modular forms move over the Hita families of modular forms. And that provides deformations into rings like this. And Mazur, in this paper, I think, just kind of writes or kind of honestly says that what he's interested in is understanding the formal algebra behind those kinds of deformations after the theory of modular forms.
Okay.
Yeah. Yeah. What I do want to say here, though, is in the case where, say, this is an isomorphism, that this really is isomorphic to some 3 ball, you could then try to account for the dimensions. Right, so I'm saying you fix your mod P representation and you look at all the lists, and there's somehow 3 individual directions in which we can look. 3 coordinates inside the ball. Now, you already have one list, right? You have your mod P representation, and you have this Galois representation. This thing's called the Tate model, and it brings that down. And the Tate model provides one dimension essentially. But what you really need to do, so you have your Tate model as a point, so that's not providing dimension. But you also have this universal character that's congruent to 1 mod P. So if you twist that representation by this universal character, you get a 1-dimensional deformation. You get 1 dimension from taking rho E twisted by the universal character. So each S kind of will give you a blown space. And then you could ask about the rest. And as I was preparing this talk, I was wondering, like, could elliptic curves provide more dimensions? And there's actually a conjecture that they can't really. And it turns out the rest of the dimensions have to be provided by modular forms or automorphic forms. So there's two dimensions that are missing, and those will come from modular forms. Okay. What I'm going to do is something that these homework tools are a challenge to prepare. And so I'm going to write a theorem on the board that might only start to make sense sort of as the week goes on. There's maybe some terminology in the theorem, but we're not going to be clear on that. Well, let me just roughly say what's going on with automorphic forms. Or automorphic representations, which I think will be the language that's eventually developed. So pi is going to be a cuspidal automorphic representation on GLN over Q. So I think this will be the topic of Rogerum's next lecture. He started talking about GL1 and GL2 today, but there's a GLN version of those things. If L is prime, such that pi is unramified. So pi L is unramified. What that means, so pi L is a representation. What is the representation R? Pi L is a representation in GLN. QL is like a local factor, or it's kind of like my prime structure. So if L is prime, such that pi L is unramified, then you have this Sataki isomorphism from the prior lecture, and there's something called the Sataki parameter, or the Sataki polynomial. G pi L of x, and let me just say it lies inside the polynomial defined over the algebraic numbers, and it comes from this commutative algebra, this commutative packet algebra that acts on the GL2 of GLN of ZL invariance on this thing. And then the theorem. Well, one of the theorems is that any sub pi is unramified at almost all primes. That you can't really say only from a local story. That's a global kind of fact. But the theorem is that if, oh yeah, now there's one more thing. So this we haven't quite covered. This we haven't quite covered, although we did talk about this commutative algebra and where a polynomial might come from. There's one more fact about pi infinity. So pi infinity is regular algebraic. These notions are extremely close to things that already came up in the GL2 story. And for GL2, it just means weight larger than or equal to 2. Well, pi infinity is regular algebraic. Then there exists a continuous semi-simple representation, rho pi. That's a Galois group valued in GLN of an algebraic closure of QL. I mean, somehow everything could be defined over a finite extension, such that when pi L is unramified, implies rho pi is unramified at L. L is not equal to P, and pi L is unramified, then rho pi is unramified at L. And the Frobenius element of rho pi of Frab L, which is a conjugacy class inside GLN of QP, has a characteristic polynomial, and that characteristic polynomial will exactly match the Sataki polynomial, which is maybe remains to be defined by the third lecture, it sounds like, or something close to it. Yeah. Next lecture, maybe. We'll see. Actually, I mean, even trying to understand the statement of this theorem last night when I was writing the notes, I had to kind of go through references to figure out exactly what I wanted to say here, to make sure everything was correct. Let me give you an example because it's good to end an example in the last minute. about what happens in GL2 and how to connect it to this question of deformation. Maybe I just put it here. I want to look at the curve x naught 11 again. That's going to be the thing that I feed into Mazur's theorem, the Mazur's deformation space question. The curve x naught 11 has good reduction away from 11. And so I'm going to take the prime to be 11 so that I don't add any extra ramifications to my Galois representation. So I'm going to take pi on GL2. When I think of GL2, I don't need to think about automorphic representation. I can think of modular forms. So I take it to correspond to Ramanujan's weight of cut form delta. And actually, squared plus 252. So this is the Q expansion. I forget whether that actually showed up. Before, I mean, I think the infinite product showed up in Lagrang's talk, and that just expanded the first few terms. This theorem, what does this theorem say? It says that there exists a rho delta and a rho pi in the Galois group over Q. It'll land inside GL2 Q11, or it can be conjugated to have integer coefficients if you wanted to. It's unramified at L different than 11, so that's going to correspond to the fact that in level 1, the automorphic representation will be unramified everywhere, and then I just always have to exclude the prime P in my theorem here. And if I write down exactly what this statement means, one thing it means is that the determinant of rho pi is going to be the 11th power of the cyclotomic character. The 11 here is the weight minus 1. And the trace of rho pi of the Frobenius element is going to be tau of L, which is the Q to the L coefficient of delta. So that somehow in what this complicated theorem is saying in the case of delta is that there's a two-dimensional representation whose determinant is the weight minus first power of the cyclotomic character. And so that the trace of the Frobenius element, which is a convex invariant, is recording the Q series coefficient of your primitive eigenvalue. Okay, and then I said I was going to connect this to Mazur's deformation space. So that's the following proposition. Rho delta or rho pi, I guess. Let me just write it like this again. And let me put a Z here so that it looks correct. And it conjugates into there anyway, so it's not a big deal. So you can take this elliptic curve that I wrote here, x naught 11. You can look at its mod 11 Galois representation, which is one of the irreducible ones. That thing has a deformation space. And the Galois representation associated with the delta function defines a point in that deformation space. I mean, this is a very fancy way of writing the following other statement. Rho delta is congruent with rho E modulo 11. Okay? Does anyone know how you prove a statement like this? You prove a statement like this by just checking the determinants are congruent and the traces of all the Frobenius elements are congruent. So let me focus, and this is what I'll end, on saying the main points, though not the only point, the main point is that you need that tau of L, which is the trace of the Frobenius element for delta, is congruent to AL of E mod 11 for every L. In theory, in practice, no, only for L up to 11 actually. Up to 11. So this is something that sometimes goes by the name of the Sturm bound. There's some fixed amount to check that, so that these Galois representations are congruent to each other. And then this is some finite computation you can make. For instance, Hall of 2 is negative 24. And A2 of E is negative 2. And I hope that those are congruent on 11. And then I think negative 1, 252 are congruent on 11. So that's tau cubed. And then you just expand out everything or use a computer. You check this kind of thing. And so this rho delta will provide another one dimension after these twist strings. Okay, so now we've got 2 dimensions of deformations. Let's see what happens next. Okay, that's all I wanted to say. For now, thank you for your attention. Yeah.
Like the theorem, the right top one is the phi is regular algebra and the comment about the GL2, this being weight is at least 2, needs to be qualified in the sense that for GL2, if you take hospital automorphic representation, they come in 2 types. They might either come from modular forms or they might come from mass forms. And this algebraic part of regular algebraic excludes the mass forms.
Except, I meant to say, what I mean by algebraic is after a certain twist, it's cohomological.
Yeah.
And so then that excludes the mass forms, no? Yeah, so the, like I said, one of the challenges for all 4 of us creating these lectures is the order in which things are said is not always so clear to the speaker even as they're speaking. And so, yeah, that the algebraic here means up to a twist that comes from the cohomology of the locally symmetric space. That's what I meant by algebraic when I wrote that theorem, and probably on we'll talk about locally symmetric spaces next lecture. In which case it will just mean GL2 here means a holomorphic modular form on the upper half plane of weight 2 and larger. And for GL1, it would mean algebraic in the sense from before, from Iron's lecture.
Attribute names to the theorem.
Yeah, timing. Should we as a group say all the names? So it goes, GL1, it goes back to Andre Bay, I think. So GL1, on the GL1 automorphic side, you have a packet character of algebraic type from before. Although in that case, it's only Dirichlet characters in the power of Bergdall norm, but maybe it's not even Bay that's doing this, maybe it's.
GL1 is all classical. So
Yeah, but it's even, in the case of just Q, it's the Kronecker-Baker theorem and things from the 19th century. For GL2, then you have Eichler and Shimura and Pierre Delis. Then there's a half century of work that involves going beyond the rational numbers, talking about Galois groups of totally real fields and Galois groups associated not with GLN, but other kinds of reductive groups that have symmetries. And there you see names like Henri Carriel, Tony Scholl, Mladen Rogowski, Andrew Wiles, Richard Taylor. Then there's a whole generation of Taylor and his students and his collaborators that are doing these amazing theorems on GLN when there's a symmetry condition on the automorphic representations. And that was enough to prove theorems like the Sato-Tate conjecture. That was really the big one. And then the fact that I can in 2022 state the theorem without any words like unitary groups, essentially self-dual, which is the symmetry condition, and any kind of qualification, is a theorem of Richard Taylor. Let me say them in order. Michael Harris, Kylin Land, Richard Taylor, and Jack Thorne. And separately, Peter Schulze in 10 years ago, basically, 2010, 2012, somewhere around there, in which they removed all the conditions you would need in theory to the point where you can just say automorphic representations on GLN over Q that have a certain condition on their infinity type. And of course, many of you, even if you're just a first year graduate, know some of the names I just mentioned. Schulze is awarded a Fields Medal for his contribution to that theorem, for instance. And depending on the mood in the room on the 4th lecture, my own mood, we may kind of approach how Schulze is really much deeper theorem than even this one. applies in the context of eigenvarieties. But that remains to be seen what happens in the next few days. Thank you, Roger. It's in my notes, like in big pink, like say the names, and then the time is running out as well. Oh, yes, sorry.
In this, this is Lozelle.
Clodell.
Lozelle made the first big step for GLN from GLN.
Clodell is even the one who identifies, I didn't say what regular algebraic means, Clodell is the one who identifies what it means. Once Clodell identified what it means, then there were theorems over the next decade proving what Clodell kind of thought. And he proved some cases wrong. Thank you. This is going on the internet, so we have to make sure we get the names right. Are there any other questions? Yeah, please.
So implicit in this, you're taking semi-simplifications when reducing, or because you said you're just checking the trace, show these representations are equal.
Yeah, but these things mod
mod
here
here
are all
are
irreducible.
Oh, they're all,
And so-
oh, you're already saying, oh, okay.
And so then, yeah, then it's gonna work like that.
Okay, yeah.
That's a good point. When you check,
Well,
I mean, but also when the determinants, yeah, once they're irreducible and the determinants are equal mod 11 and the traces are equal mod 11, then they're isomorphic representation. And there's a whole thing I didn't mention, which I think is implicit maybe in your question about the role of the Chabatarov density theorem and theorems in representation theory, and why, for instance, I only need to write down characteristic polynomials or Frobenius elements to describe everything. And that's something I'll build into another lecture. It's really foundational to the theory, but it didn't necessarily fit in every discussion of Galois representations. Thank you for your point. Okay, well, if you have stars on your paper, please show them to Andre. Andre will answer all your questions. Who asked the question about the universal deformation? That was you?
Yeah.
Okay, let's talk about it for a minute.
Okay.
I mean, you can come up here and talk to.
Right, so the CB cross has cohomological dimension 1, so shouldn't this just be like the space should be parameterized, it should just be like dimension should just be like H1, shouldn't it just be like an H1 of CB cross like that?
The universal deformation of the trivial character, say, is a power series ring in one variable.
Yeah, it's like H1
What
of CB.
I'm worried
cross.
about is that that's not the variable, that somehow p times the variable. Like you have, not every power series ring in one variable is the same power series ring in one variable.
It's a key.
And
Oh, okay.
so I'm just not sure that I've captured every deformation or whether. That's what I wanted to be careful. Like in practice, what it should be is the universal deformation of the trivial character should be the group algebra on this procyclic group.
Right, yeah. Oh, yeah, yeah.
And maybe that's exactly what I wrote down, and I'm just not. And I just didn't say it very well.
So what you're saying that like it should be the group algebra on this, and then like each of the specializations is just like composing this, or sorry, what are you saying?
So what I'm saying is that. And what I decided, like, there's something I've internalized.